A very good morning to all the students of semester 3. We are going to start the class of Business Mathematics and Statistics from today. Your paper code is G 3.3. The total marks allotted for this paper is 100, out of which there will be 10 marks for internal assessment and semester end examinations of 40 marks. In total, 50 marks for module 1, which will have 5 chapters, which you can see on the screen. Similarly, module 2 will consist of the statistics paper, which have an internal assessment of 10 marks and semester end examinations of 40 marks, in total 50 marks again. So in this module, you again have 10 chapters. You have 5 and 5, all total 10 chapters. For your reference, you can refer these following books. Okay, so I will be basically teaching you the statistics portion, the module 2. So thus we will be starting with chapter 6, correlation and association. So far, we have already studied univariate data. That means data which have only a single variable or a single characteristic, like height of an individual or weight of an individual. And we have computed different measures on it, like mean, median, mode, or mean deviation about mean, skewness, variance, kurtosis. But now, in correlation and regression, our focus is on bivariate data. So, since the name suggests bivariate, that means it consists of two variables. So, it has two characteristics, like, for example, height and weight of a class of students, or ages of husband and wife, or monthly incomes and expenditures for a number of families, or amount of rainfall and yield of a crop, amount of fertilizer used and yield of a crop, dosage of insulin, blood sugar, maximum daily temperature, expenses on advertisement and sales of a product, scores in admission tests and final examination, or marks in statistics and marks in statistics, reading ability, spelling ability, heights of fathers and sons, vocabulary size and age, marks in mathematics, and heights of a class of students. So all these type of data is bivariate data, since it has two characteristics or two variables taken together. Okay, so we deal such type of data in correlation and regression. These are usually represented by capital X and capital Y, or it can be represented by any of the variables from A to Z. Now, since there are two variables, so they should have some association between them, or some relation between them, okay, which was not in the case of and univariate data. So now we come across this term correlation, which actually measures the strength of the relationship, and regression, which helps us predict or forecast one variable given the other variable. Now, mind this, correlation always deals with linear relationship. The word linear is extremely important. It has a relation, but that relation is linear. Now, if there is a linear relationship, then it can be positive or negative. Positive in the sense if we see some tendency in one variable to increase according to the increase of the other variable, then their relationship will be considered as positive. However, if one variable decreases and the other one increases, or vice versa, then the relationship will be negative. Okay. So if we go to the above example, example 6 is a negative relationship. Example 6, which states dosage of insulin and blood sugar level for a group of diabetic patients. Why this relationship is negative? If you increase the dosage of insulin, the blood sugar level automatically decreases. So hence, one variable increases, other variable decreases. Hence, the relationship is negative. However, example number 7 is positive. Example number 7 states dosage of insulin and reduction in blood sugar. That means as the dosage of insulin increases, the reduction in blood sugar, there is a reduction in blood sugar. Okay, hence the relationship is positive because one variable increases, the other variable also increases. Or if one variable decreases, the other variable also decreases. Now, there can be a third kind of relationship, which states that there must be no relationship at all or zero correlation. That kind of example is example 14. Or 15. Marks in mathematics and height of a class of students. This is an example. This is an example of no correlation or zero correlation because marks in mathematics has no influence on the heights of a class of students. Next, we move on to scatter diagram or scatter plot. Scatter plot or scatter diagram is basically a diagrammatic representation of bivariate data. So the bivariate data, the examples we considered above, if they are plotted on a graph, then it will be known as a scatter diagram. Now, how is the scatter diagram helpful to us? It displays the nature of relationship between the two variables, how each pair of values is plotted as a point on the graph paper. So in a scatter plot, we basically look for the overall pattern and for the striking deviations from that pattern. Overall pattern is described by the form, direction, and strength of relationship. That is, whether it's a linear, non-linear, positive or negative, strong or weak. Now, as I said before, there is an x variable and a y variable. Each of these two variables, they take up n pairs of observations or n number of observations. And how those points look like is given over here. This is how the points look like, xi and yi. That means the first point is x1, y1. Second point is x2, y2. Third point x3, y3. Like this, right up to xn, yn. So these type of points are plotted on the graph paper, which gives you the scatter plot or the scatter diagram. Now, here we think of the variable x as the explanatory variable. X is known as the explanatory or whereas y following are the examples of some scatter plots. Number one, we have y on the y-axis, x on the x-axis. And when we have a set of points like this, we state the linear correlation. Next, when we have this type of points, we state the relation to be weak positive linear correlation. Next, when we have a strong negative or linear correlation, this is how the points appear on the graph. And when we have a perfect positive linear correlation, this is how the graph looks like. The points are exactly on the line. Fifth, perfect negative linear correlation, where the points are in the downward direction and falls exactly on the fitted line. Next, if there is no relation at all, the points appear in a circular manner. Seventh kind of relationship is a curved relationship, which looks like this. And finally, a perfect quadratic relation appears like this. So these are your basic diagrams of a scatter plot. In this paragraph, all these relationships are being explained. Next, we shift our origin from 0, 0 to x bar, y bar. Then, the points for which x values are higher than x bar and y values are higher than y bar will lie in quadrant 1. That means this particular quadrant. Similarly, the points for which x values are less than x bar and y values are greater than y bar will lie in quadrant 2, as you can see from this relationship. The points having x values lower than x bar, y values lower than y bar will lie in quadrant 3. And finally, the points having x values higher than x bar, y values lower than y bar will lie in quadrant number 4. And this entire relationship depicts positive correlation. Okay. The next graph gives you an idea of the negative correlation. And finally, zero correlation. For the first graph, or positive correlation, we observe that more points they lie in quadrant 1 and quadrant 3. That is, there are more points for which xi minus x bar into yi minus y bar is greater than 0. And few points are there for which xi minus x bar into yi minus y bar is less than 0. Similarly, for negative relationship, there are more points for which xi minus x bar yi minus y bar is less than 0. So there are more points for which xi minus x bar into yi minus y bar is less than 0. So this is in case of a negative correlation. So in summary, xi minus x bar into yi minus y bar seems to be a reasonable basis for a measure of degree of association, which is positive for positive linear relationship and negative for negative linear relationship. In figure 3, we introduce no quadrant has significantly larger or smaller number of points compared to the other. That means there is no linear relationship. However, the positive and the negative values of xi minus x bar, yi minus y bar tend to counteract one another, producing a value of summation xi minus x bar, yi minus y bar close to 0. So what we do is we divide the sum products of deviation unit to make this measure unit free by the product of the standard deviations of the two variables. This leads to the most popular measure of association between two variables known as Carl Pearson's correlation coefficient, which is denoted by R. So R is known as Carl Pearson's product moment correlation coefficient. Actually, the formula for R, after you standardize it, becomes something like this. Okay. However, to deal with this Carl Pearson's product moment correlation coefficient, we need to first study covariance between x and y. Now, covariance is for a set of n pairs of observations xi, yi on two variables x and y is given by COV for covariance between the variables x and y as 1 by n summation xi minus x bar into yi minus y bar. On simplification, like if you break these brackets, curve of xy is given by 1 by n summation xi yi minus x bar y bar. Now, if you remember what x bar and y bar is from your previous semester, these are x is the mean of the xi variables, y bar is the mean of the yi variables. Okay. Now, from this formula, how we are obtaining this is given below. So curve of xy is this. If you break the brackets, you will get 1 by n summation xi yi, x bar yi, y bar xi, and x bar yi with the consecutive signs in between. Now, if you take the summation inside the brackets, you'll get 1 by n summation xi yi minus x bar into 1 by n summation yi minus y bar into 1 by n summation xi plus 1 by n summation x bar y bar. So we know 1 by n summation yi is basically y bar and 1 by n summation xi is basically your x bar. So finally, the formula reduces to 1 by n summation xi yi minus x bar y bar. Now, it should also be noted that curve of yx is also equal to curve of xy. Okay, that means covariance is independent of the change of origin and its base. Next, we quickly move on to some results on covariance. Result number 1, curve of AB is 0, AB being two real constants. So in place of x and y, if you take A and B, this is a relation which you have done in semester 1 again. X bar becomes A, Y bar also becomes B. So curve of AB ultimately is 1 by n summation A minus A into B minus B, which is ultimately 0. Result number 1.2 is curve of x comma c is 0 or curve of c comma y is 0. Similarly, if you are substituting c in place of y or c in place of x, you are getting 0. Result number 1.3, curve of e1x plus b1y plus c1. So if you have a linear relationship of x and y, then finally what you get is a1 variance of x. If you remember your variance formula for the first semester, okay, then you get a1 b2 a2 b1 curve of xy plus b1 b2 variance of y. Okay, so look at the coefficients carefully. A1, A2 is with variance of x, B1, B2 is variance of y. And these are just getting interchanged. A1, B2 plus A2, B1 curve of x, y, where your A, B, C's all are constants. What you basically do is you take Z equal to the first linear relation, W equal to the second linear relation, and then compute their means, which is Z bar and W bar. So next is very simple. You just substitute that form in covariance of ZW, which is 1 by n summation A1 xi plus B1 yi plus C1 minus its corresponding mean into A2 xi plus B2 yi plus C2 minus its corresponding mean. What you get is something like this. You're taking the constants common and you are left with xi minus x bar, yi minus y bar also from here. Then multiply this, you're getting summation a1 a2 xi minus x bar whole square a1 a2 plus a2 b1 xi minus x bar yi minus y bar plus b1, b2, yi minus y bar whole square. Next step, take the constants out and take 1 by n and summation inside the brackets. So you are getting this. Finally, a1, a2, variance of x1. If you remember, as I said from semester 1, this is your formula for variance. So this becomes your variance of x. This you have learned just now. It's the formula of covariance xy. And finally, this is your variance of y. Okay. So in particular, if you consider this curve of ax plus by, similarly give you AC variance x, AD plus BC co xy plus BD variance of y. Then number two, if you have a change of origin and a change of scale, which is denoted by this, what you do is 1 by BD curve of xy. Okay. And finally, if you have variance ax plus minus by, you will get something like a square variance x plus minus. So if you have plus, this becomes plus. If you have minus, this becomes minus. Plus b square variance of y. And finally, variance of xy, x plus minus y, equal to variance of x plus minus 2 covariance xy plus variance of y. So we stop today here now. We'll continue again on next Monday with correlation and regression. For the time being, you will again have your class tomorrow at 10:30 sharp. After end of this week, you will given the assignments which you have to submit in by email. Any queries or any questions, you can mail at hcc.mathstat@gmail.com. Okay. Thank you. Have a good day.